So I want to welcome all of you to today's lecture. Today we want to look at application of clustering, and we are applying it to the financial industry. So we are seeing the significance of that in real market systems. Okay. Now, investment managers all over the world, they select correct assets, correct securities, like stocks, bonds, real estate, mutual funds, all of these. That's their job. They monitor the performance, they manage the risks that a particular investor will bring so that you do not lose your asset that you have. They do all of that. They adjust the holdings. Whatever you put in, they adjust it, in response to the market conditions. And whatever the client's needs are, they try to do that for you because there is an interest, there's a charge they are charging you. So they have to manage your portfolio very well for you. That is the job of investment managers. Who are some of the world's largest, some of the world's asset managers? Which companies are the top asset management companies in the world? Those who manage your assets. Well, one of them, the biggest one of all, is BlackRock. BlackRock. Now, Richmond, have you ever heard of BlackRock before? Have you heard of BlackRock, Linda?
No, sir.
So it's a $10 trillion company. And you've not heard of them?
No, sir.
Yes, sir means you have. So that is it. That is an assets company now. Now, Vanguard is another one. Fidelity Investment is another one. JP Morgan is well known. Goldman Sachs is well known. McKinsey, several of these companies are well known. And all of them manage assets. They manage, they're one of some of the largest asset managing companies in the world. Now, why am I telling you this? Because they are the ones, because they have a lot of clientele, they need to be able to organize their clients into particular investor profiles. They need to organize them in such a way that this particular group is different from that group by virtue of the similar characteristics that this group will have. Some people are risk averse. Some are risk takers, risk lovers. Others are risk neutral. So by knowing which particular risk profile the person is, you can categorize them, classify them into different clusters. But it's not easy because you're talking about having millions and millions of clients, millions of clientele. That is where clustering comes into the picture. And as you might know, clustering is an unsupervised machine learning technique. What it does is that it groups similar data points together. And what do we mean by data points? For us to have a data point, you must have X1, X2, X3, X4, X5, X6. Put together, that becomes one data point. But normally when we want to demonstrate it in a 2D diagram, we use just X1 and X2 to illustrate the data point. But what they do is that they group the similar data points together based on their characteristics without knowing the actual labels beforehand. So they don't know, but based on the characteristics, they will eventually be able to now put them together. I want you to see clustering as finding hidden patterns or structures in the data. And in the process of finding that, you will be able to group customers together by behavior. You can segment regions. Okay. For example, if you realize that most people are all speaking the Ewe language, you can segment them all together by virtue of the language. You can organize search results. You can create pattern recognitions. anomaly detections, pre-processing, all of these are ways by which clustering can be applied. Okay. Now, we need to see areas where clustering technique has been applied as an unsupervised machine learning technique. And one of them is customer segmentation. It's a very popular, well-known one. It is where you group the customers, by the way they buy a particular product. For example, if you go to Amazon, there are some sort of customers, they go to that place, they buy a book. The next time you buy a Kindle, the next time he buys an audiobook. So you are able to now know some customers, the way they are behaving, their purchase patterns, and then you can group them together. You can also use clustering in image segmentation, where you divide an image into regions of similar colors or textures. You can use it in grouping news. So do we still have PMP? Did you guys come to meet PMP news? Some of the news relate to entertainment. Some are sports. Some are politics. Some are music and dance. So you are able to now group these news items, cluster similar articles or emails together. For example, you can use it even in emailing spamming, where you are able to identify that this is a spam, this is not a spam, by virtue of the title of the email. You can also use it in recommender systems, like where you cluster users, okay, or items to find similarities. I spoke about Amazon. There are several AI-powered tools right now that will predict user preferences right now, and then they will suggest the relevant items, whether it is a product or movies or music, they'll suggest. So if you like action movie in Netflix or Spotify or Amazon or YouTube, you will realize that each time you log in, they will tell you, these are the movies we are recommending to you because of what you have seen. So sometimes they will tell you that because you saw this movie, this one has been given to you. They don't sit down. There is an AI-driven system using a recommendation system that has been able to create this for you. Clustering helps to do all of that. So that is what we mean by clustering. Before, I wanted to understand clustering itself, because the last time you guys told me that you would love to have an intro. I wanted to understand itself. I also want to show you a simple example of it. Then we will now look at the practicals next time. So what are the types of clustering? You see, there are several ways, techniques you can use to cluster. The most popular one is the K-means clustering. The K-means clustering is very well known. We shall look at that today. Another one is the hierarchical clustering. Sometimes it's known as the agglomerative clustering. And there's agglomerative and there's a divisive. Okay. There is also the graph-based, the message passing, some popularly known as affinity propagation clustering. We'll look at that. Affinity propagation. Now, because Python is very good at each one of these, sometimes you can let Python give you all of them, so that quickly, after you've used all of them, you can select which method is the best. And there's a way to know which method is the best. Okay, so that is a affinity propagation. It tries to find examples by iterative messaging passing. There is also the DB-scan that will group points that are closely packed together. And then it will identify the abnormal ones that are not within the particular centroid or clusters or means. There is a model-based clustering, the Gaussian mixture models. That is also able to handle these clustering as well. So there are several of these clustering methods that one can actually look at. There is the PCA, because PCA, principal component analysis, or distributed stochastic neighbor embedding. Okay, these two can be used to reduce high dimensional data that has multiple dimensions, because as you walk in the world, you walk and you are looking at things from multiple dimensions. You can bring it into a 2D dimension, like X and Y graph, Cartesian plane graph, or a 3D dimension, like a potentially cuboid. And then you can visualize the clusters. Okay. Now, the distributed stochastic neighbor embedding that you have, that is a dimensionality reduction algorithm, which reduces the dimensions. You know, it does this by modeling the probability distribution of neighbors around each point. You know, so that they call it neighbors, T-distributed stochastic neighbor embedding. So the 10 neighbors refers to the set of points closest to the given point. You can use that as well to do your class. Now, which one you are going to use will depend on the nature and the structure of the data. So let's look at one of them. K-means, the most popular, widely used one as well, because that will set the foundation for the others. Of course, I'm not going to teach you every one of them. There's a whole lot of things of that. But I'm going to give you the basic understanding of the K-means in the simplest way, so that you can be able to understand it well and can appreciate the others on your own. So what is the goal of K-means? Well, the goal of K-means, as it stands now, and is the most popular, is to divide a data set into K distinct, non-overlapping groups. So the clusters or the groups, they do not overlap. So when you say that one group is small and another group is large, there is nobody within the small who looks like is large. And there's no one like large who looks like is small. There is no overlap. There is no intersection. In such a way that the WCSS, which is known as the within clusters sum of squares, the WCSS, that within cluster sum of squares, and it's sometimes called inertia by the software, that within cluster sum of squares is reduced, is minimized, where every data point belongs to the cluster with the nearest centroid or the nearest mean. And I'll show you an example. This one is theory, and you will appreciate it very well. Okay, so what is it doing? The key word here is minimizing. What are you minimizing? You are minimizing the distance of a data point to the mean. So if you have a particular data point here, a particular data point here, a particular data point there, you identify the mean of each of these data points. For example, suppose you have a data point like this, and then you have a data point like this. I'm going to use a different color for you to tell me which one is going to be the mean of this. One, the mean of this is going to be A here. The mean of this is going to be B here. Or the mean of this is going to be C here. Which one of these do you think will be the mean of the blue data point? Which one? Is it C? Is it B? Is it A? Which one would you say that is the mean of the data point, the blue data point? Are you guys here?
Yes, Doc, I think it's B.
Yes,
Okay. Guys, I need you to be talking to me, because that's the only way. Otherwise, you see me moving so fast and you're not going to understand anything. The only way I can slow down for you to understand is when you respond or ask a question. All right. So that is it. That mean, after you've identified the mean, you realize that there is a distance from the data point to the mean. And you want to reduce the distance. And in the process of reducing the distance, it's like you are moving the data point into the mean. That is what the k-mean, that's why it's called means. That's what the k-means is trying to do. So the objective function is that you have a lot of things, actually. You have, it's a minimization function. It's an optimization where you are minimizing a set of points assigned to cluster K. Okay, you are minimizing. So you notice that you have this K, which starts from 1 all the way to capital K, which means that there are a lot of these means. But before that, you see that you have xi. Xi here refers to a data point. A data point. So a data point where you have, on the Cartesian plane, you have y-axis, you have x-axis. So let's say that you have something like 0.2 and 0.7. And 0.2 and 0.7 is able to create a point called A. So A is xi. So xi here, in fact, let me not even use A. I can just say that this is known as x1. So I is 1. So xi is one of the data points that you have there. Now, so you have x1, which is made up of 2 coordinates, x2, x3, x4, and on and on and on and on and on. Okay, good. You got that. Once you have these x's, you now find the mean of them. And the mean of them is the mu k. Okay. That is the mu k. Now, the mu k here, you are later going to realize that the k here is going to be for one group. So maybe you have x1 like this. You also have x2. There's x4. There's x5. There's x7. There's x5, and all of that. But between x1, let me use a different. Between x1 and x2 and then x4, they create one of the k's. So they create k equals to 1. So that is, one of the k's. So that makes one cluster, one group. And then you have, this one here too, that come together, become K2. That's a second group. So what you do is that, what this function is doing is that the xi here is trying to find each data point minus the mean, of that particular group. You take the absolute value of that, you square it, and then you sum that across the number of k's that you have. And then you minimize that, sum of squares of all of these data points. Now, the k here, the mu k, I told you is a mean, but we call it the centroid. Let me just show you here. We call it a centroid. So the mu is the centroid of that particular cluster K, or CK, is the mean. It's also a number, okay, and it's a mean. And then the gap here, that distance here is we call it the squared Euclidean distance. So you can see that we are taking the absolute value and then squaring the absolute value. So the squared Euclidean distance between that point xi and that cluster center. That is what you're doing. So you are minimizing the distances for all of them and sum them. Let's get into the steps better so that you can appreciate k-mean, for the last time. Sometimes some of you guys will say, oh, I know it, it's k-mean, you do this, k-mean. Because you're using the software, sometimes you don't even know what is behind the scenes of this software. So what is the k-mean actually doing? The first step, there are 4 steps in executing the k-mean. The first step is to specify the number of clusters. You see, K-mean clusters does not require you to let it determine the clusters for you. No. You got to choose ahead of time how many groups do you want to have here. So that's the first thing. You specify the number of clusters you want. It must be based on the literature or that particular industry or that particular analysis. You will come out with what others have used or something. But there's another way. There's a technique where you will also be able to know how many clusters to choose. When we come to the practicality, you see, we'll use some elbow effect and some silhouette analysis to be able to get it. After you selected the clusters, you randomly, haphazardly select the K data points at the initial cluster centers. You select each one of them. So you are going to select the new one, which is the centroid for the first cluster, mu 2, which is the second cluster center, and then all the way up to mu K, depending on how many Ks you have. So that's the first, and we call it initialization. Initialization, because you got to be able to come out with the centroids. Now, after you've done that, you do assignment. You are going to assign each data point, the xi, each of them, to the nearest centroid. Of course, you will not do an assignment where you are assigning somebody to a centroid that it doesn't really belong to. No. You got to assign it to the nearest centroid. So there will surely be some centroids, all right? As you can see up here, you have U1, U2, and all of this. So the centroids are many. So you got to assign each data point to the centroid that it is closer, it is sharing similar characteristics with, so that you can cluster center and then to be closer to it. Now, the process of doing that is a sort of an argument. We call it argument of the minimum. So you assign xi to cluster ck such that the k, so that grouping is arg minimum. So it is an argument of the minimum. Now, this is a mathematical operation that will find any input value. So we are looking for an input value that will minimize the given function we had before. So what this argmin is trying to do is that it is answering the question, which input gives the lowest output of the function? Okay. Which input gives the lowest output of this function? Because we need the minimum input that will maximize the existing output. So this assignment process will divide the space based on something we call the Voronoi cells. Now, normally some of these things, if you don't understand, you just have to, read them. Just have to read them about it. Now, Voronoi cells, it's not a term here, actually. It is a term, that is not within this area here. It's a kind of biological term. Okay, it is the region where each point is closer to one centroid or one average than any other. So you are telling me that I am an Ewe. You bring somebody who is a Ga, and you bring somebody who is an Akan, and you bring somebody who is Fanti, and you bring somebody who is, so remember, Ewe, Ga, Asante, and Fanti. Which of them are you likely to put together? You're likely to put Asante guy and the Fanti guy together because they share similar regions. They share something. So that is their Voronoi cells. Okay. So that is what this is going to be based on. So you do the assignment. After the assignment, you now recompute, we call it update. You recompute the centroid of each cluster. So each cluster, you will now find the mean of each cluster there. And how do you do that? It's a very simple thing, okay? So the mean here, the centroid of each cluster is going to be 1 divided by the clusters, okay, multiplied by the sum of the data points. Sum of the data points. And then that's it. Okay? So you get the mean of all of the data points in any particular cluster. Okay? You get the mean of them. And then you repeat the process. Why are you repeating the process? Okay? You are repeating the process, which is called iteration. You are repeating the process because you want to achieve 2 things. 1, you want to get to a point where there is no more, change in the centroids. So the centroids no longer change significantly. So we get to something we call a convergence, where the centroids no longer change significantly. Because when you calculate the mean, the centroids and they change, it means that what you had before wasn't correct. That's the first one. That's why we repeat. We also repeat because the maximum number of iterations should be reached. So when the maximum number of iterations has been reached, then you know that you have achieved the exact number of groups that you wanted to achieve. That's why you do the repetition. During the repetition, you'll be able to achieve that maximum. So, yeah, there you go. Just as I said, so the process will guarantee that convergence to the local minimum of the objective function is achieved. And that local minimum of the objective function becomes the Euclidean distance that we spoke about there. So the k-means is basically using this Euclidean distance, which we know already in normal mathematics. Okay? The data point minus the centroid. You are taking the square root of each one of these elements. Okay? The k-means is just using this Euclidean distance to find the minimum of the numbers. Sometimes if you don't want to go using the square root, you rather use this formula, which means that you are rather taking the squared Euclidean distance, you are trying to find the lowest level. So you are finding the loss of the Euclidean distance. Every step that we have already discussed, every step that we've spoken about, remember, is doing something. What are they doing in every step? Every step that we have spoken about is trying to reduce or keep constant the value of the objective function, which we said is the within cluster sum of squares, the WCSS. Okay. So you are trying to reduce the value of the objective function, okay, so that you can get the minimum distance, whereas the convergence will have been achieved. When I start a simple example, you will get a picture. Don't worry at all. Okay. Now, in Python, the code for calculating the k-means is this. So from sklearn.cluster, you will import the k-means, and then you will use the fit function. You will say that k-means is equal to k-means into bracket n clusters, okay? And then you define that, and then you will now run the fit of that. You can do a couple of hyperparameter tunings. We'll talk about that when we come to the practicalities. But I want you to understand the hyperparameter tuning is basically like when you have a microwave. And when you do the microwave, you will notice that the microwave has got a time. But even though it has a time, you have to also put it at whether you want the thing to do slow cooking, which is low, or medium cooking, which is medium, or high cooking, which is high. All of them will still have 10 minutes, 10 minutes, 10 minutes. Okay. So you are tuning the thing to your taste. So when you do any Python analysis, okay, you use hyperparameter tuning to tune the thing. But the question is, in k-means, what are you tuning? You are tuning the number of clusters and the centroids. You are checking, you are adjusting to see whether that is what you want. You are also checking the maximum iterations of the algorithm. And then finally, you're checking the number of times the algorithm will be run in case the means are changing. The final result will be the best output of the defined one. Okay. So we'll use some couple of hyperparameter tunings So every analysis, let's say you are doing cluster regression analysis, whether you are doing ordinary least squares or lasso regression or elastic net regression, you know, or any of the other regression, range regression, whatever regression you are using, everything you are using will have its own different hyperparameter tunings. Okay. And for k-means, the hyperparameter tunings are these three. Let's take an example, a very simple example. So you have data points. You have point A, you have point B, you have point C, you have point D, you have point E and F. And you have some variables, okay, that will be able to, you can plot this. You know that. You can decide, you can scatter plot this actually. If I were to, I don't know how, I can't believe that I didn't even include the scatter plotting of this. I should have. But again, suppose that you have an XY graph like this. Okay. And here is Y, and here is X. If I want to plot A is going to be 1, 2. So if this is 1 and this is 2, they will meet somewhere here. And that will be my A. If I want to plot B, it's 1, 4. So 1 is still here, down here. 4 should be double of this, so go up there. So B will be somewhere that. If I want to plot C, 1 will be still here, okay, but Y is 0, so it will be at that same point. So C will be on the axis of X. That's it. Okay. So now how about if I want to continue with this? I want a different color. Let's say I want to plot D. Okay, if I want to plot D, D is 10 and 2. So 10, I need to go all the way right toward here. Okay, so you need to have something like 10 here, okay, and then 2. Okay, 2 will be on the same level as the A, so that will be somewhere here. So now you have here to be D. Sorry, you have here to be D. I'm sure you guys can understand me. You can plot, can't you? You can see where I'm going, can't you?
Yes, please, we can see.
Good.
Yes,
So
sir.
you use this approach to do all your plotting. So you scatter plot the thing. Now you have your data point for each of the elements. Okay. So what are we plotting? Let me just close. So you have each of these data points. Now, the X, the capital X here is a kind of a random variable. Okay. That is like the technology set that is having each one of these data points in there. Each one, every one of them is part of that plot. Now, we want to do something. We want to cluster these into K. You remember I told you that K is determined ahead of time. Okay. So we want to cluster these into K groups. And the groups we want to do is 2. If you look at this thing, we cannot classify them into 3. Anyway, we can try 3 and see later on. But from the onset, we want to group these things into 2. You can say that you can look at it with your eyes and get some kind of grouping from it. But let's assume you don't even know. And then you chose that, let's categorize all of these data points into 2 groups. Okay, so you chose 2 groups. How do you go around it? Well, they are going to follow the 4 steps. And guys, I want you to be calculating alongside with me. It will help you to understand this thing once and for all. If you don't do it by hand, you will not understand what's going on. And one of the things I've seen is that when you do things at hand, it will help. So we are going to initialize the centros. That's step 1, initialization. Okay, what does that mean? Initializing the centros here means we are going to randomly pick 2 points as the initial central, as the initial means. Okay, that is initial. So if we here, we are going to randomly pick 2 points because we said that we want K groups. So we're going to pick, there are how many points here? There are 6 different points. We can choose any 2. We can choose A and F, We can choose B and F. We can choose this and this. We can choose this and this. We can choose this and this. But sometimes with some kind of I, oh, and by the way, we are doing this by hand, but most of the time you won't do this by hand. But I just want you to know that that's what is happening. So I want to decide to choose. Remember, I am randomly picking 2 points and making them the mean. I don't know what the mean is, but I'm picking 2 points. So I want to pick the first mean to be 1 and 2. Okay. I want to pick the first mean to be this point. That's my first mean. And then, so I'm going to call this one mu1. Okay, so that's going to be my mu1. And then I'm also going to pick this one to be my second centroid, mu2. Now, you might be asking me, why did I choose this one? But I told you already also that this is random. Okay, so you can also do your own random. Okay, that's why we are iterating the process. So I've picked these two here. But personally, by looking at it, there's a reason why I picked these two. If you're smart, you know. I know you know. If you don't know, you can ask. Because it's accent that will show that you know. Anyway, so I picked this. So for point A and from point D, I've selected 2 points as the initial centroids. The next thing will be the assignment. So let's go to where I selected them here. Let me just delete this. So here, I've done my selection here. The first one, I pick 1 and 2, which is the new one. For the second, I pick U2. So I've just selected point A and point D as my initial centroids. I need to do my assignment. What does that mean? The assignment step is where you calculate the squared Euclidean distance from each point to this mean, to this centroid you have selected. So I'm going to take each of the points here. Okay, I'm going to take point A, which is 1, 2, and see how far it is from the mean I've selected, which is 1, 2. I'm going to take point B, which is 1, 4, see how far it is from the point, the mean I've collected, which is 1, 2. So I take every one of them, every one of these 6 data points, and see how far each one of them is from the 1, 2. Then I take every one of all these 6, and I also check how far each one of them is from the 10, 2, okay, using the formula for the Euclidean distance. So that's basically what you are doing. You are assigning, you are calculating the squared Euclidean distance from each point to the centroid. Okay, so I've done a table of this so that you can appreciate. Now, this is where the entire meat is. So if you don't understand something, just let me know. That formula you saw in there is what I'm using. So when you look on the top right, the formula you are seeing on the top right, the absolute value of the data point minus the particular centroid, that is what I'm doing here. Okay, minus the centroid. So what were the centroids? The first one was 1, 2. So you can see that one up here, 1, 2. That is for the first centroid, the U1. The second one, you forget about the second one, the U2. Let's focus on this first one. So I take the first data point. If you can remember, the first data point was 1 and 2. So I take this first data point, which has the coordinates of 1, I minus the centroid I selected. The centroid 2 has got an X value and a Y value. So I do 1 minus that X value. I square it, because remember this one here. This one here is the centroid. As you can see, it is this one on the top right here. Let me use a different color. Okay. This one here is a center, which is the same as this UJ here. So I do the first number, which is 1. The actual values were actually 1, 2. So this is the A coordinates. Okay. This is the coordinates of B. These are the coordinates of C. These are the coordinates of D, and then on and on. So I take each one, minus the centroid 1, okay, plus, okay, the second number minus the second element of the centroid. And then I square it and I find the answer. We go to B. The B's coordinates were not 1 and 2. They were 1 and 4. But the centroid U1 was 1 and 2. So I take the 1 minus the 1, I square it, and then I take the 4 minus the 2, which is the second centroid element, and I square it. When you simplify this, you're going to get 4. And then you do the same thing for every one of them is going to be using the 1, okay, and after which you square. And every one of the data point is going to use the second element of the centroid, which is the 2. And then you do that, and then you calculate the Euclidean distance for each one of them. That is assignment. Now remember, we said you should do U1, and you should also do U2. Okay, so U1, we got this. But even before we go to U2, you can see something here. You can see that these values are closer to each other. So they are more likely to be clustered together. And you will notice that these values are also bigger, far away from the first values, but they are also closer to each other. So they are likely to be clustered. Okay, let's go to the second one. The second one is where we chose the D, okay, as the initialized centroid. So the mu2 was 10 and 2. Again, once again, they are the ones going to be inside this element here. The 10 is going to be there, and then the 2 is going to be there, and then each of the data points minus this centroid that you've selected. Okay, you simplify it, and you see that the first ones, they have numbers that are closer to each other, and then the second ones, they have numbers that are also closer to each other. So based on this, just looking at it with your eye, you will notice that if you use this U1, this first element, A, B, C, have something in common. The numbers around them are common. When you use the U2, the numbers around them are going to also be common. Okay. And so we will assign cluster 1 to this first group, and then we will assign cluster 2 to the second group. Guys, do you understand? Do you understand?
Yes, sir.
Yes, sir.
If you don't understand, you can just let me know, because this is the best way that you can ever understand K-means clustering. Now, we're done. We finished, but hold on. There's something interesting here. We got to recompute this based on the assigned clusters, okay, which we have done. What we need to now do is that we take cluster 1, which was A, B, and C, and we found that we need to find the mean. Okay, so we take the A, B, and C, the coordinates that are already in there. And what we are going to do is that we are going to pick the element of the A, okay, the first part, the x's, the element of the B, the x's, the element of the C, the x's, which is the 1, 1, 1. Then we find the mean of that. Then the 2, 4, 0, we also find the mean of that. So we've done that here. The 1, 1, 1, we find the mean of that. Okay, that is what we mean by recomputing the centroid based on the assigned clusters. We are recomputing to see whether we'll get back what we selected. So we do that, and then we realize that this U1, when we take the mean of this, okay, the 1, 1, 1 will give you 3. 3 divided by 3 will give you 1. It balances the original mean that we selected. And then the 2, 4, 0 will be 6. 6 by 2 will give you 3. 6 by 3 will give you 2, which is that. So eventually you can see that this one agrees. It doesn't conflict with the U1 that we randomly selected. Okay, you stay there. Then we go to the cluster 2. The numbers we found, the 10, 10, 10, we find the mean, and that will give us 10. Okay. And then the 2, 4, 0, we find the mean, that will give us 2. Again, this agrees So the centroids have not changed. The centroids that we selected originally, when we double check, it's like simultaneous equation where you put everything back into the equation to see whether you will get the equal to the right-hand side of the equation. When you substituted it, you still get a right-hand side of, in this case, the centroid. They haven't changed. So it means that convergence has achieved, or we've reached a convergence. We have achieved convergence. And that's it. That means that our two groups we selected was correct. And it also means that those A, B, C will truly cluster themselves into cluster 1. And what do you call it? The D, E, F will cluster themselves into cluster 2. This is like a pre-processing approach, an exploratory data analysis that we sometimes do to be able to do something. Suppose that you want to classify the number of banks in Ghana into foreign banks and domestic banks. This can easily help you. Even if you don't know that this particular bank is foreign and this particular bank is domestic, you can pick maybe the capital, the market capitalization or the minimum capital requirement of every bank. And by clustering processing, you can see that the minimum capital requirement for every bank, some of these banks have a similar minimum capital requirement, different from the foreign ones, which also have a similar minimum capital requirement. So based on that, without even having any knowledge that the policy from the central bank is for foreign banks to have this number, the clustering will tell you that they are having this, and therefore that will agree with this. Now, in the real software, this is what K-means is doing, what we just did. K-means is doing this in higher dimensional space, repeatedly assigning points and averaging the results, just as we have been doing. So what we are going to do right now is that you've seen by hand how the clustering was done. What we are going to do is to do this simple work in Python so that you can also see exactly what Python is doing. Once you begin to understand this, you don't understand the theory here. We're going to go to Python because when we come next time to the practical, I'm not going to go through theory again because now you have large real data set. In fact, in your thesis, any work you'll be doing, you'll be using real large data set and you would have understood what is happening behind the scenes. Okay, so let's do that. I'm going to go, so I want you to open your own Python. I'm sure you have it. And then we can look at that. Let me first close the entire screen sharing and then I reopen it. Next time when I'm going through the real practical, I will be fast because I expect you to understand this. Okay, so this is the K-means clustering. Okay. So we've already seen that the goal of K-mean is to partition the data set into K-distinct non-overlapping clusters where every data point belongs to a cluster. And the cluster, it doesn't just belong to a cluster, but a cluster with the nearest centroid, the nearest mean. First thing you do is that you specify the K in advance, and we have some 2D points that I've shown you here. To do all of the analysis, we will use matplotlib for plotting the program, and then we will also use scikit-learn for the K-means implementation. Okay, how do you start? First, you got to use NumPy to import your data set. Okay. You know all of these already. If you don't know, you tell me. Okay, this NP NumPy is used for numerical operations. Okay, matplotlib is used for data visualization. I don't know why this thing keeps coming. I need to just close it. Okay, it's used for data plotting, graphs, and all of that. And sklearn is used for clustering algorithms and all of that. But scikit-learn itself is a whole chunk of library that has a lot of other things it does. But within that, you can do clustering. So what's the first step? If you remember the first step, that was initialization, basically. So we are going to define our data set. because we are inputting the data itself, we are not using pandas per se, but we are using NumPy. Pandas is when we have the data set and we use that, we bring it from Excel into this, which is what you will normally have. But here we create an array to define the data set. That's the first thing here. It's fairly simple. If you don't understand, you ask. The next is to apply the k-means with two classes. So we've selected two clusters. Now, the most important thing is this formula here. So you need to understand this formula. We called it k-means. We called it k-means. Let me just, how do I take this thing off? Because it just keeps popping up. Just a second. Anyway, so once you have this, you see that what I've just highlighted is the actual formula package that is calculating the k-means. What you see on the left here, that one, you can use any other term for it, that I just decided to use k-means. The n clusters here, okay, is where you specify the number of clusters you want to use. And you choose this by yourself. So we chose 3. Now the initialization here, we remember we initialize it by using 2 point A and point D. The coordinates here are what we are using. So we are using the coordinates. Okay. So this will do the initialization data, which points that you want to use. Then the n initial here means that you are going to run once, because the centroids are fixed. The means are fixed, and because the means are fixed, you are doing this run and only once. We are not going to run twice or 3 times. As for the random state 42, we know that it ensures that if you ever want to reproduce the work, you can do the reproducibility. So you run this command and give it into the command window. After that, you run the model by fitting the model. So this will compute, the second one will compute the actual k-means clustering on this array, okay, or this data set that you have. It will do that calculation. It will do all the key steps that we spoke about. Everything, it will do it. Okay, so all the steps that we spoke about, this command will do it. That's why it is called fitting. It will assign, it will update, it will repeat, all of that. Okay, in case you have forgotten the, what do you call it? In case you have forgotten the step, the first step is the initialization, which is specifying the clusters and randomly selecting. That one wasn't part of the fit. That one was here. Okay, that one was here. So that initialization was, but then in the assignment, the updating, which is a step 2 and step 3, assignment, updating, and then finally the repetition, they are all inside this command. Okay, the fitting command. So you run that, and then the final step is when you want your result. Okay. So if you want your results, it will give you the results. Now, what results do we want? First result we want is that we want him to tell us the means, to see whether the means agree with our pre-selected ones. So this command, centroids. So you are commanding that I want you to give me the centroids. Okay, I want you to give me the centroids of this k-means clustering. Okay, so you see that we have cluster.centers. That will give you the final centroids after the convergence has been achieved. And then it will give you the results. And the output should match the initial centroid in the sample, the one we hand computed some few minutes ago. You can also tell it to give you the labels, because this k-means.labels is a very nice thing, because what it does is that you are telling it that I want you to tell me the names you have given it, you know, like the labels, what labels. So you have group 1, group 2. Remember in our own, we use group 1 and group 2, if you can remember. But here, you know what Python is doing is that it's not giving group 1 and group 2, but it will rather give you the result of group 0 and group 1, which is the same thing. So the first group, the first 3 points should be given a group of or cluster of 0. Then the next or the last 3 groups should be given a cluster of 2. So you are telling it to do the grouping for you. Once you print these 2 results, this is what you get. So these are the centroids, which agreed with what we had. Then you printed the labels to give you. So it tells you that point A is in group 0, point B is in group 0, point C is in group 0, D is in group 1, and then on and on. But I decided to also draw a graph. And the graph is good because it helps you to see what is happening. So how do you plot the graph? Well, it's a basic scatter plot. Okay. Basic scatter plot, you use some colors. Okay, this will plot the data point. It is colored by some clusters. And then you are telling it to use the data points. We are using these colors to do the work. You are indicating that the mean should be given a color of red. Okay, with that marker, the labels of the mean should be given a color of red. And those will be surely the centroid. If you want the legend, you have indicated that the legend for this should be given. So when it comes to the bottom, the data point is part of the legend. And then there's mean is also part of the legend. Okay, so you've indicated that. But even with the data point, you see that you have indicated that the data point should be colored differently so that when you look at group 0, you see that they are colored like purples. And then when you look at group 1, they are colored like yellows. So the coloring tells you that these groupings or these data points are grouped by colors. That's the point. They are grouped by colors. And then the centroid or the mean are the stars, the red stars, which is what you see here. And that is it. That is how you generate the K-mean clustering. Remember, the whole idea is to be able to know this. That's all. And you've done it. It creates this one. And that's it. Okay. Now, the interesting bit here is there are 2 ways to evaluate the performance of this clustering algorithm. We shall look at this practically in the real life. But I want you to know a bit of it. How do you evaluate the performance of this method, this algorithm? You have to use some approaches, and we're going to look at each one of them. There's some bit of mathematics behind them, but I don't want us to go into the mathematics. I want you to just. You can use something called the sum of squared errors, which is also called inertia. You can use that to determine whether your approach is a good approach. And not only this one, in fact, even if you are doing affinity propagation, okay, or agglomerative clustering, all of them, you use the same approach to tell. So this is the approach you use to select which one is the best for you. And we shall practically do this in investor world, when we meet next time, which I think is tomorrow. So the sum of the squared errors, okay, is also called a within cluster sum of squares. What it does is that it measures the total square distance between each data point and the average of its assigned cluster. Basically, we've done this already. If it is smaller, it means that the clustering was good. So you want a smaller, because it's an error, isn't it? And a lower error is good. A 0 error is best. So if it is smaller, it means that the points are very close to the centroid, or the means. But when the data is large, you have to use something we call the elbow effect or the elbow method. The elbow method will tell you the optimal number of clusters to select. It is at a point, we'll look at this next time. It is at a point where the curve is coming, but it begins to bend. Okay, so the point of first bend of the curve, okay, it will match maybe clusters like 4. This one will match clusters like 6, you know, and this one will probably match clusters like 0. So at the point of the bending, it looks like an elbow. When you take your elbow and you bend it, that point is the point that will give you that. So with this sketch I just made, it will tell you that 4 is the number of clusters you should go for, and not 6, and not 0, and not 2, but 4. So the elbow method will help you to choose the optimal, the correct number of clusters. So you are using the errors, what do you call it? You are using the inertia, which is the sum of squares of errors, together with a graph. Remember, the elbow method is always a graph to help you make your decision. Now, the second approach to decide whether your performance is good is the silhouette score. It tells you how well each point fits with a cluster compared to the others. So if you take point A, how does it fit with the cluster compared to all the others? Okay. And the silhouette score is between -1 to +1, just like a Pearson's correlation coefficient. If it is +1, that one is good because it means that they are perfectly matched. Okay, that point is perfectly matched to its own cluster. So if for A, the value is +1, it means that A is perfectly matched to be in cluster 0. If the value is 0, that's not too good because it means that it's on the boundary between the two clusters. So you have cluster 0 and you have cluster 1. And then this particular point, let's say point C, is having a silhouette score of 0. That means that the guy is not in cluster 0 and is not also in cluster 1. He's kind of in between. He's not sure which group, which clusters he belongs to. And of course, if it is negative, it means that you are actually in a wrong group altogether. Okay. You're probably in a very wrong group. So what we are going to do is that we're going to calculate the sum of squares and the silhouette score for our sample example, and then we check. So I'll go through the same process, but we just introduce everything is as the same here. But the step 3 here is where we bring in the silhouette score. So you can see that SSE is k-means dot inertia, which is the sum of squared errors. Okay. So we calculate the sum of squared errors, and then we calculate the silhouette score. And then this will give us a score. So SSE is a sum of squared error. The SIL score is a silhouette score. We print the results, and then we get these values. So the sum of squared error is 16. The silhouette score is 0.7. Now, just looking at the silhouette score, okay, should tell you that we said that if it is +1, then you have perfect. It's not +1, but it's close to 1. Okay, 71%. So that tells you that it's good. Okay. Now, the sum of squared error here, if you look at the interpretation, it is 16. Okay. And it shows that it's low. Okay. You know, sometimes somebody will say that how low is low? It's low because it is, if you have to look at it in terms of percentages, it's low. It's low. And normally, the two of them will move in the same direction. And this one clearly tells you, the silhouette score clearly tells you that it's high, it's close to 1, which shows that we have a well-separated clusters. We have cluster 1, or cluster 0 and cluster 1. So these metrics are confirming that the clustering that we chose worked very well on this toy, this hypothetical data set that we have. You can try k-means of 3. Let's try that and see. Let's try k-means of 3. Okay, so I'm just going to change this one here. And then run this. The shape of the initial centroid does not match the number of clusters. So you can see, let me just go backward. Yeah, So it just tells you that that 3 clusters will not work. Let me just go back here and see whether if I change this one, it will give me the same situation. Yeah, it gives you the same thing. The shape of the initial clusters does not match the number of clusters 3. So clearly, it tells you, say, the thing is not as you would have wished to do. So we go back to the 2 clusters, and there you go. That gives you the perfect, way to look at it. So that is how k-means work. Now, another approach, I'm just going to go back to the slides and show you the second approach. Let me just go back to that before I talk about the affinity. We are not calculating the affinity propagation. So let's look at the pros and cons of the k-means first. It's very simple. As you can see, it's very simple. It's very, very highly applicable to real market system. You can see that the convergence was good. Whatever we chose before matched the initial one. It has something called linear scalability, to a large data set. You can scale it. And it also produces clusters of an even size. You can see that the clusters are even, like 3 in the first group and then 3 in the other one, unlike having 2 in the first group and then 1. So that's an advantage of it. You can also realize that the disadvantage is that you have to know the exact number of clusters. That's it. You have to know the exact number of clusters. Like we have to know the K before we start. Okay. And then we have to tune in this K. Now, I'm not doing that tuning here. We'll look at that practically next time. Okay. That K hyperparameter, you have to tune it. And also, it doesn't guarantee that you can find the global optimum. And it's also sensitive to outliers. Suppose that some of the data points were far away. It could bring about, we can try it, but suppose there was a data point like 106 somewhere, it would drag the whole matter because that outlier can change the centroid, which will now affect the results. So it's sensitive to outliers. It's just like mean. Normal mean is sensitive to outliers, unlike median. Median is not sensitive to outliers. The means are sensitive to outliers. So that is it. Now, the affinity propagation is also a very powerful tool for clustering, but it doesn't require you to specify the number of clusters beforehand. Unlike the k-means where you need to specify the number of clusters. It will identify the points that are closer to each other. It will create clusters around those points, using something we call message passing. And then it will select the cluster centers from the actual data point. Now, the affinity propagation, all of these other ones, we'll look at it in the real life one. We'll look at this later. But for now, I want to take you back to the Python so that we see how the affinity propagation works on this sample data, because this sample data is the last time I'm using it. So, and you're going to see something interesting here. If you look at so you import the data, everything is as usual, but affinity propagation starts from here. So if you look at this, AP is affinity propagation method. Okay. We set the random state, we apply the fitting. The results is going to be like this. We show the results, we give the labels, we print the results, and we do the plotting. Okay. Everything as it is before, just that this is affinity propagation. Now look at the cluster centers it gave us. It tells us that the cluster centers are 0 and 3. Now let's go back here. So if you look at this, we have this data. Look at that. It is telling us that the cluster centers are 0 and 3. Okay. Now, first of all, and it's also telling us that the cluster labels are the same thing as we had before. That estimated number of clusters. Now, if you check this, it tells you don't have to specify the clusters beforehand. That's a good thing we said. It will rather tell you how many clusters you should have. And it says that the estimated clusters are that. When you look at the graph for this, it is very, very similar or the same as the previous one that we had. Okay, it's very, very similar. So if you, and again, this is because the data set is small, and so it's very easy to manipulate and look at them. But when we come to the real one, you will see that sometimes the affinity propagation approach will differ from the original approach. And you will also note that the centroid that it has given, that centroid is not in any of the data points. So if you check the centroid, this one says, what is that? The previous one says 1 and 2, and then 10 and 2. Okay, 1 and 2, and then 10 and 2. But this one picked two coordinates that are 0 and 3. So if you look at this thing, 0 and 3 will be somewhere here, up there. 0 and 3. It will even be on top of this. Okay. So you have to use the running before you can actually get it. But the good thing is that both of them now gives you the same one. So what you have to do for you to be able to know that you are on the right track is you can calculate this. I didn't do that, but you can calculate this, the silhouette score for this to see whether that is the same thing. Let's try it and see. Are you guys following? Are you with me? Because sometimes you have to be with me.
Yes, sir. Sir, please, we are with you.
So you have AP here. I'm sure it's going to be the same thing, but let's. So let's see. Okay. Made a mistake here. So you have affinity propagation has no All right. So with
Yeah,
this,
I'm sorry, sir. I was calling Linda.
it's
She
okay.
dropped
You
out.
mute
I was calling
yourself.
her.
It's okay. Mute yourself. Don't explain. Okay. So if you check the codes, you are able to get the affinity propagation. You are able to get the silhouette score here to be the same thing, and that gives you the same value. Okay. So it means that both of them are good. Okay. Well, the good thing is that both of them leads to that beautiful convergence. So it's a very good way to check that. For this example, both of them give you the same result. But one of the things you will see, and you see that in our next exercise, and next time we meet, you see that it's not all the time the affinity propagation approach will marry the k-means approach. And in that case, you have to make a decision. And I'll teach you how to make a decision when there's a disparity between the two. But in this simple case, we've been able to use or classify, data points into groups. Now, remember, if you have something like Netflix and you are doing a lot of classification and you have a customer group of 2.7 million, classifying is very, very important. So this one is just 2. Sometimes the classification will require that you even have 17 different clusters. 20, 10, and not just 2. We'll look at that practically in our next meeting. So that brings us to the end of the entire Kabuda. Next time, what we are going to do is we are going to look at a real life case study, about clustering investors. First of all, you need to know why investors, if you're a bank or you're an investment manager, or you have an investment management company, you have to cluster your investors based on the similar characteristics, which will simplify and standardize the investment management process. Because once you cluster them, you will know those that are high risk customers and those that are low risk customers. Machine learning can be used to group investors based on different factors, like based on their age, based on their income, based on their risk tolerance. You can cluster individual investors on that. So clustering is very important. It can affect the allocation of their assets. It can affect rebalancing. Rebalancing means realigning the portfolio weight. So you put more weight on stocks. You put less weight on maybe something else, crypto. You put more weight on real estate and things like that. That's rebalancing. So it makes it very powerful tool for faster and effective investment management. So if somebody has millions and billions of assets and tells you to manage it, you have to know, because there are many and you can't do everybody. So now you got to develop a machine learning algorithm that will put them into groups. So when you are helping them in groups instead of helping them individually, because most people will have similar characteristics and you want to help them. So in the case study we shall look at, we will use clustering method to identify different types of investors. That is what we shall do in our next exercise. And class rep, I'll encourage you to remind me to give you the data set so that you can understand, because this is a kind of a thesis. This is kind of a thesis. I have the Python code to give you, but I want to give you the data set to just play with first. The data can be obtained from the Survey of Consumer Finances, which was conducted by the Federal Reserve Board of the US. So that's the data set that we will use. That is a data set that we talk about, and the whole thing is about portfolio management. And one of these asset management companies you are seeing here, like BlackRock or JP Morgan or Goldman Sachs, that's what they do. Okay, what they do is that they organize clients, investors, into particular investor profiles, so that they'll be able to know how to help each one of them. We shall go, next time we meet, we are going to go through the problem definition, loading the packages, exploratory data analysis, preparing the data, finalizing preparing the data, evaluating the models, okay, looking at the training and the testing, identifying the evaluation process, model tuning, using several hyperparameter tuning, which are specifically focused on the grid search, and then we'll finalize the model. All of that. So we'll do that next time. Any question?